right. Okay, thank you for joining, Kilat and Rasini. Can you see my slide?
Yes, doctor.
Okay. So last week we discussed about the applications. So this week we will discuss about the transmitters. Okay. So same like last week, if you have any questions, just stop and then just voice out your question. Okay. All right. So moving on to slide number 2. So so last week was our introduction and application of photonic devices. So this week we will talk about transmitters, and next week I will cover receivers. Okay. So I'd just like to give, this is more like a refresher, the difference between light, photonics, and also optoelectronics. So as I've explained last week, light is comprised of, is actually basically the electromagnetic spectrum, where the energy, the photon energy E, is equivalent to hc over lambda, where h is the Planck's constant, c is the speed of light, and lambda is the wavelength of light in meter. Okay, and I've also explained last week that the frequency can range from the gamma ray right until the extremely low frequency. So the frequency can vary from very large frequency to very low frequency. And similarly, the wavelength can be very small, 1 pico meter, right until 100 megameter. And this corresponds to the energy 1.24 mega electron volts and very low value of 12.4 pico electron volts. Okay, so this is about the electromagnetic spectrum. So the visible light spectrum, it occupies only a small portion of the overall electromagnetic spectrum. Is right over here, which is from 400 nanometer to 700 nanometer. And in photonics, we are interested in the visible light region. That means the light that we can see with our eyes. And also the regions just above, which is the ultraviolet. And also the region below the visible light, which is the infrared. Now, why is this so? This is simply because it is easy to generate and detect light in these three regions. So generate means lasers, detect means detectors or receivers. Okay, the human eye, it is sensitive to light with energy, HV stands for energy, photon energy of less than 0.7 micrometer or equivalent to larger than 1.8 electron volts. Okay, so if you look at this diagram over here, so this is the relative eye response, okay, and we can see red, orange, yellow, green, blue, and all these colors, but with our bare eyes, we can't see infrared and also ultraviolet. So beneath here, there's semiconductor materials, which are used to obtain these wavelengths. So as you can see, some of them cannot be seen with our eyes, but these are semiconductor materials. Okay, and this is the corresponding wavelength and also the energy, photon energy. So this diagram over here shows that for three different materials, which is gallium arsenide, indium phosphide, and also gallium antimony. So this is this is the lattice constant, and this is the photon energy. So you can see that we can tailor these materials, different types of materials, region 1, region 2, region 1, region 2, and also region 3. So region 2 and region 3. So this is for gallium indium arsenide phosphide, gallium indium arsenide antimony, aluminium gallium arsenide antimony. So by changing the molarity of different materials in the semiconductor, we can tailor the band gap. Okay, you can see that the band gap changes. So let's, for example, this is gallium phosphide. Okay, the band gap, the energy is about 2.3 something. But when you change it, you start adding, you make it into arsenide, you replace the phosphide with arsenide, the band gap drops to 1.5. So similarly, this is called band gap engineering. We can get the different photon energy by tailoring different materials. We call it the molarity of the materials. We tailor the molarity and get the corresponding photon energy. by getting the corresponding photon energy, you can get the corresponding wavelength. Okay, this is another figure which shows the band gap energy, the photon energy, and also the lattice constant. So all these different materials, so these are the common materials used for visible light. Okay, so moving on, so these are some properties of light. So the effects of materials on light is mainly dependent on the refractive index value. And so I hope from your previous classes you still remember what's the meaning of refractive index value. Reflection, or we call it pemantulan in Malay, refraction, pembiasan, dispersion, penyerakan, total internal reflection, TIR, pemantulan dalam penuh, interference, diffraction, pembelauan, scattering of light, penyelerakan, and also polarization, which is polarisasi. So a few figures just to explain what is it. So refraction is pembiasan. So this is two types of material. One is both with different refractive index. Maybe it's air and water. So a typical experiment that you commonly see is a pencil. When you put it into water, it will look bent. Okay, that is the effect of pembiasan or refraction, because light in a certain medium, this is air, where the refractive index is 1, it moves in such a way. But when it meets water, which has a refractive index of 1.33, which is higher than air, light is refracted. Okay, it moves, it changes, it doesn't become a straight line anymore. This is reflection, what you see in mirrors, and reflection is what is used in lasers. So you have a material which can reflect the light totally. All right, nothing is refracted, it is totally reflected. So this is a mirror reflection, specular reflection, and also diffuse reflection, where light is almost scattered in a few places. And dispersion, using a glass prism, you split white light into its different components. Okay, dispersion. Total internal reflection, another phenomenon which is used in lasers, where the light which is inside the laser must experience total internal reflection, and it stays within the active region. Okay, it doesn't go out, it doesn't refract, it doesn't, so it's totally reflected within the medium. This is diffraction grating. Else than using a prism, a grating can also be used to split light into its different components. This is interference, covered by Dr. Dila, where light comprises, if there's two wave of light, and when they meet with each, yes,
can refraction and reflection occurs at the same time?
Yes, of course. Yes, it can occur at the same time. It can. It's just how many, what's the percentage of refraction and what's the percentage of reflection based on the material. So certain materials, they allow full reflection, no refraction at all. That's how you get total internal reflection. That means nothing gets at, this must be at a certain angle and a certain refractive index. You see, above the critical angle, all the light is reflected back. But if it's below the critical angle, the light can still be refracted. That means some is reflected, some is refracted. So you can see there's a percentage here. Okay?
Okay.
All right. So back to interference. So interference, you can have, if two peaks meet with each other, you get a double peak. And if two minimums meet with each other, you get a minimum intensity. So you'll get light, no light, no light. So this is the basis for light modulation. That means on, off, 1 and zeros. You modulate light to transmit signals. The other property of light is scattering. So if it meets a body of water or something which has got no particular shape, it can be reflected or refracted in various areas. This scattering effect can happen in a Raman scattering. Okay, if you want to know the molecular dimensions of a particular atom. Okay, and polarization, light can be polarized. You can use a polarizer So as you know, light has got many components in it. So if you only want the linear component, you use a linear polarizer. So only the linear light will go in. If you have a circular polarizer, so two components will go in. And if it's elliptical, so the signal will also be in elliptical form. So these are the ways that we can control light. Okay, moving on to luminescence. So last week there was a question from Faris about luminescence. So I thought I just put up a slide. So basically luminescence is the emission of photons. So these photons can be in either the ultraviolet wavelength, visible wavelength, or infrared, depending on the material. And if the light is emitted because of friction, rintangan, so we call it triboluminescence, okay? When it is caused by the absorption of ultraviolet radiation, visible light, or infrared, then we call it photoluminescence. And photoluminescence can be divided to fluorescence and phosphorescence. So photoluminescence, it lasts less than 10 nanoseconds. And phosphorescence is lasting more than 10 nanoseconds. This is longer, this is shorter. And you can see fluorescence is the fundamental effect that happens in fluorescent lamp, lampu Kalimantan. It is also the basis also in LED, but LED has got another component which is electroluminescence. There is also electric current in LED. So it has got two effects, photoluminescence and electroluminescence. So when light is formed because of heating, you give it heat, we call it thermoluminescence. And electroluminescence, when you apply electric current or field. And cathodoluminescence is when you activate light emission by electrons. This is the basis in cathode rays, or if you remember those days, the TV, it's called cathode ray tube. All right, so that is the basis of cathodoluminescence. So I just put up a picture showing you different types of method where light can be emanated. So this is cathodoluminescence. This is from a mineral sample. So it reveals the presence of zone calcite and saddle dolomite in boxwork breccia. Okay, and this is sonoluminescence. Is from sono means sound. Is from sound. Multi-bubble sonoluminescence created by an ultrasonic horn immersed in liquid. Okay. Chemiluminescence. This is due to chemistry from a light stick. D is bioluminescence from a biological component. So in this particular case, this is deep sea Siphomedusa. Okay, another common one is firefly. Yeah, api-api. Yeah. So the biological can convert to light luminescence. Electroluminescence. So this is electric field across a pair of parallel wires. And last but not least is photoluminescence. This is from colloidal cadmium selenide quantum dots. All right, so it emits yellow light. Okay. So just now was about light. So photonics is, as I mentioned last week, you can play around with light. What can you do with it? You can generate light, you can amplify, transmit, modulate, and also detect light. And in this slide, I will go through about how you generate light. Okay, and next week we look at how you detect light. And what is optoelectronics? So optoelectronics, you study electronic devices that interact with light. So interact means emitting, absorbing, modulating, or switching it. And light is any electromagnetic radiation. Electronic usually means made of semiconductors. And emerging technologies currently are like plasmonics, graphene, carbon nanotubes, phosphorine, silicon, or silicene, this is a typo, CENE, hexagonal boron nitride, and also molecular devices. So the interplay between quantum electronics, nonlinear optics, physics of semiconductors, and transport phenomena. So it is important not to get lost and to see the coherence and connections between different subjects. you still see my slide? Okay. So the main devices in optoelectronics is semiconductor lasers, LED, detectors and solar cells, non-linear optical systems, novel devices like carbon-based and plasmonic. And basically the plan of study for each kind of these devices, we look at the basic principles. Okay, the basic principles, the examples, and also the challenges and outlook in the future. So basically, it comprises of integrated photonics, nano devices, quantum optical systems, which is about cryptography and also communications. So we always look at the applications in mind, but the emphasis is on the physics of it. Okay, so I guess for this week and next week, this may be the most important slide. Okay, if you understand this slide, you understand the whole lecture. So this is the properties of light and electron interactions. So basically, photons is given by this equation, E equals to hv, which is h is the Planck's constant, and v is the speed of light in a particular medium. So basically, based on conservation of energy, the photons can be converted to electrons and holes, and electrons and holes can be converted to photons. So when photons are absorbed and become electrons and holes, this is the basis for photodetectors. So light is absorbed and electrons and holes are formed. All right. So this is the basis for photodetectors. When electrons and holes recombine to produce photons, that is the basis for recombination or emission, and is the fundamental principle for LED and also for lasers. Okay, so for LED, there is no external simulation, so light is emitted. For lasers, there is an external stimulation, so we call it externally stimulated. So one photon produces two photons, whereas in an LED is a spontaneous emission. Okay? So this is the basis of photodetectors. Light is absorbed, spontaneous emission, basis for LED, stimulated emission, basis for lasers. Okay? So light or photon energy can be converted to electrons or hole, or vice versa, when energy is absorbed or emitted. Okay, so basically light can be reflected, transmitted, absorbed, or it can be scattered. And this shows the relation between the refractive index. How do you define refractive index in a particular medium? It is C over V, which is speed of light in vacuum and speed of light in a medium. Okay, N equals to C over V. Air, N is 1, water, N is 1.33. So far, so good?
Yes.
Can understand? Okay, great. Okay, so now I go in deeper. It's more and more into physics. Okay, so stay awake, don't sleep. Okay. Okay, so light sources or optical transmitters. So in photonics, normally we use semiconductor-based light sources such as light emitting diodes or LED, superluminescent diodes, and also lasers. So I will cover these two mainly, but I will also put in some slides about superluminescent diodes. Other light sources are single photon sources, fluorescent lamps, cathode ray tubes, plasma screens, fiber lasers, and spacer or plasmonic lasers. But mainly this lecture is about photonic devices, so I go very deeply about LED and also laser. The rest is just a single slide just to give you the overview. Okay. All right. So as I mentioned, light emitting diode, LED, and laser. Laser stands for light amplification by stimulated emission of radiation. Normally, there are two methods of amplification. There can be a gas laser or a solid state laser. Solid state is normally semiconductor based. And some of the common semiconductors that are used are gallium indium phosphide, aluminum gallium arsenide, indium gallium arsenide, and This was already shown earlier, the relationship between the photon energy and also the wavelength. So basically you just, the wavelength is defined as 1.24 divided by the photon energy in electron volts. So these are different semiconductor materials and the corresponding wavelength which it can emit, all right, the corresponding wavelength that it can emit and the band gap energy. Okay, as I mentioned earlier, we can tailor the molarity of the materials to get different band gap energy and different wavelength. Okay, so let's look at the physics of it. So we have electrons recombine with holes to form photons. So this is the circuit for a light emitting semiconductor junction. So semiconductor junction basically is a p-type. Is attached to an n-type junction. P-type means there's a lot of holes. N-type means there's a lot of electrons. So two layers are next to each other. Now let's look at the conduction band and the valence band. So Faris, Yusuf, and Azman, are you all in the Microsoft team?
Yeah.
Azman, is it?
Nah, Faris.
Faris, okay. So Faris, maybe you a bit blur when you listen to all this because it's. Are you okay? You can understand or how? You don't?
Yeah, actually, I made diploma in engineering.
Okay, all right. So you understand semiconductor physics?
Yes, a little bit because I
Okay.
forgot a lot.
Okay, okay, very good. I'm so happy. Okay, is Azman here as well? Azman? Azman not here. Okay. All right. I think Kinjian, Kelat, Lokesh, and Rasini, no problem, right? To understand?
No problem, doctor.
Okay, so you should know the basis of semiconductor physics. So basically, in all material, you have all semiconductor material, you have what we call conduction band and valence band. All right, and when there is zero voltage, what happens is the holes and the free electrons and free holes, they are all in their own places. They are in the P and the N. Nothing happens. And you can see that the band gap energy or the difference in energy is very high. So they cannot go here, the electrons cannot go here. So they cannot recombine. But what happens when you supply it with a forward voltage? You can see that the band gap energy has reduced. All right. The step is very small. So what happens is electrons and holes can move to each other's region and they recombine. Okay. Electrons and hole can recombine and photon is emitted. So photon is emitted. This is the principle of energy conservation, because when electrons and holes recombine, energy is emitted as a photon. Okay. This shows a double heterostructure laser where you have the N region, the P region, and the middle is what we call the active region. So the active region is the region where light is emitted. Okay. So in this, you can see the energy band gap here is very high, 1.35. Here is 0.95 and here is 1.3. So the electrons and holes will recombine in the active layer. And if you see, there is a principle of, there is also a principle of refractive index, where the refractive index is low, or the refractive index is high in the active layer and the refractive index is low in the outer layer. If you remember well from your past lectures, this is the basis for total internal reflection. So when light is emitted, it just stays inside this region, okay, because it cannot go out because of the lower refractive index in the outer layer. So when light stays in the active layer and we use a mirror to continue to reflect it back and forth, and when it reaches a certain threshold, it gets emitted out. Okay, so there's two things here. The first is the band gap energy. You need to make sure that the active layer has got a smaller band gap energy. And the second thing is the light. How do you constrain light to remain inside the active layer? So we call this the carrier. How do you how do you capture the carriers, and how do you capture the light. Two effects, because you want electrons and holes to recombine to form the light. So you need to make sure the energy here is low. So you use different materials so that you get low energy for recombination. So once they recombine, light is formed. How do you make sure that the light remains inside this active layer? You use refractive index of the material. Okay. So this is also about bandgap engineering. We change the aluminium molarity fraction, and when you change it, you can see the light, it changes from a direct material, direct bandgap, it becomes an indirect bandgap. Okay, the bandgap energy increases and the wavelength reduces. Okay. Okay, this is just a further explanation from just now. Same, you have for for equilibrium, you have the P region, you have the N region and P region over here. This is the active region. So you can see the bandgap is very, very high without voltage. But once voltage is supplied, you can see that the electrons can flow to the active region. And when electron flow to the active region, it can recombine with the holes. And when it recombines, energy will be dissipated as a photon energy. So this is the basis of emission. So again, it shows different wavelengths for different types of material. Okay, and this figure right here shows by doping the material, we can tailor the bandgap. So here, the gallium arsenide phosphide, the Y is less than 0.45. And for gallium phosphide, when you dope it with N, you can see that it has reduced here a bit. The bandgap has reduced. And when you dope it with aluminium, you can, this is for silicon carbide, you can tailor the valence band to be higher, so the bandgap energy is lower. Okay. Okay, now we move on to LED. All right, LED is actually a chip of semiconducting material. It doped with impurities to create a PN junction like just now. So when the LED is forward biased, charge carriers, electrons and holes flow into the junction. When an electron meets the hole, it falls into a lower energy level and releases energy in the form of a photon. Like just now, right? It releases the energy. The wavelength of the light emitted and therefore its color depends on the bandgap energy of the materials forming the PN junction. In indirect bandgap materials such as silicon and germanium, the electrons and holes recombine by non-radiative transition, which produces no optical emission. Okay, so these are different types of LEDs, red, green and blue, also white. Okay, the materials used for the LED have a direct bandgap with energies corresponding to near-infrared, visible or near-ultraviolet. So again, the schematic of it, holes and electrons, they recombine and light is emitted. Okay, so basically from a higher energy level, it goes to a lower energy level. So due to conservation of energy, energy must be transformed to something else. So it's transformed into light. Okay, so for band structure, I think those who are from FSC maybe are well versed of this, but I still go through because we have Faris. Okay, Faris, band structure. So we use the Bohr model. It's a planetary model that defines the allowed energy levels by equating the centripetal force equal to the Coulombic force. So the Bohr model of the atom defines the allowable energy states where the electrons can occupy. Pauli exclusion principle states that no two electrons can exist at the same energy level with the same spin at the same time. Together, these principles help to explain the band structure of a semiconductor. The Bohr model of the atom assumes that electrons revolve around the nucleus in discrete orbitals. Each electron is at a discrete unique energy level or state. Okay, so this is a nucleus, and you can see electrons around the nucleus. We call it orbital electrons. And nucleus actually comprises of proton and also neutron and electrons circulating around the nucleus. So in order to change states, the electron must undergo a quantum leap to another allowed energy state. That means from high energy state, it go to a lower energy state. So they always seek the lowest energy level. And the Fermi level is the energy level when all electrons are in the lowest energy states, which occurs at absolute zero. So this defines the valence band. Remember just now we had conduction band and valence band. Conduction band simply means an energy level which is higher than the Fermi level. So at absolute zero, all electrons are in the valence band. Okay, so this is the conduction band, this is the valence band, and this is what we call the band gap energy or the energy gap. So when electron moves from higher energy to lower energy, you have light is emitted. So so as temperature rises, the electrons become more active due to thermal energy imparted by the surrounding temperature. The average amount of thermal energy is considerably less than Eg. So there's also heat involved, but still the majority of it is in terms of photons. As the temperature rises, the electron becomes more active due to the thermal energy imparted by the surrounding temperature. The average amount of thermal energy is considerably less, and it appears that none would be able to jump the gap to the conduction band to be available for current. However, thermal energy is not equally distributed among the electrons, and only a few will possess sufficient energy to appear in the conduction band. Okay, so this shows the energy gap. So actually it's not a parallel line like just now, it is actually periodical. So the energy differs along the density of states. And there are two types of band gap. One is what we call the direct band gap, and the other one is a indirect band gap, where the minimum of the conduction band is not aligned to the maximum of the valence band. Okay, so direct band gap semiconductors, so the minimum and the maximum are directly above each other. Okay, and in a direct band gap semiconductor, electrons at the conduction band minimum can combine directly with holes at the valence band maximum while conserving momentum. The energy of the recombination across the band gap will be emitted in the form of a photon of light. So we call this radiative recombination or spontaneous emission. Okay, and the prime example is gallium arsenide. So this is direct band gap semiconductor, where the minimum and the maximum are aligned directly above or below each other. So in indirect band gap, they are not directly under each other. Okay, so this is indirect band gap. So an example of this is silicon. All right. Now many research works they try to do a intermediate transition where it will transmit somewhere here to this level and then transmit down. Okay, for silicon. Compound semiconductors, this group includes the 3,5 and also 2,6 compounds. So in a compound semiconductor like gallium arsenide, doping can be accomplished by slightly varying the stoichiometry or the molarity, the ratio of gallium atoms to arsenide atoms. A slight increase in the proportion of arsenide produces N-type doping. A slight increase in the proportion of gallium produces the P-type doping, because you need carriers to produce photons, so you need to dope the material. So this gives a list of materials, all right, from 3,5 compounds, 4,4 compounds, and 2,6 compounds. I think, okay, 4,4. So some of them are indirect and some of them are direct, and this is the band gap energy for these materials. So you can see here silicon carbide is indirect. Silicon is also an indirect band gap material, and the commonly used are normally 3,5 and also 2,6 materials, right, as lasers. This is an anatomy of a LED. Okay, basically you can see the anode here and also the cathode. Okay, this is where the current or the voltage is supplied. And if you look carefully, the laser is actually over here. And this top part here is what we call the epoxy lens or the case. There is a wire bonding to bond the anode to the end doping of the laser. And there's also a semiconductor die, of course. All right, this is the semiconductor die. And then you have the end wheel, the post. This is what we call the lead frame, the flat spot. okay, to determine which is cathode and which is anode. So basically the cathode will have a shorter electrode compared to anode. Okay, so this is cathode anode, and there's a bonding wire as mentioned just now. And as you can see here, this is the semiconductor chip, right? So there's an active region here, and the light is emitted out. So this is the light, and there's phosphor inside here. And once it hits the surface of this epoxy dome, the reason why it's round like this is to make sure that light doesn't reflect back into the chip. Rather, they want it to go out. So if the surface is in a dome shape, the chances of light going out is higher. Yes?
Scattering, right?
Yes?
The light is scattered, right, Doctor?
The light is scattered out. The light is scattered out. But when it meets this dome here, if you see the dome is made into a circular shape, the purpose is so that we don't want light to be reflected back inside. We want it, because it's a light, right? We want it to go out. So that's why it's made in the shape of a dome. If you don't make it into a dome, the light will get reflected back into the chip. All right.
So when the light go out, it's meaning refraction, right?
If the light is going out, it is called scattering and refraction both, because it meets to another material outside here, right? It's refracted out, and it's also scattered out.
Okay.
Different material, right? Here N is different, here N is different. And so it's scattered and also refracted out. But of course, certain percentage also gets reflected back in. All three happens. If you remember here, yeah, all three can happen, right? It means this is the dome. So some will get reflected, transmitted. This is what you want to happen inside the LED. Some will get absorbed, some will get scattered. Okay, the most important is you want transmission to happen. So you must make sure the percentage is high over here. Reflection must be small, absorption must be small, scattering must be small. Okay, Faris?
Okay.
Yeah. Okay, so okay. Right, so this shows the various layer inside this chip here. Okay, this chip here, if you take a cross section of it, so you have the BL contact, so you have a silicon substrate, you have the P-type germanium, P-type germanium, the N-type germanium, N-type germanium, and also N-type silicon. So light is emitted out, and then you have the signal contact over here, right? So this is the actual SEM image of a LED. Okay, this chip, this small chip over here, this is what it looks like. So light is emitted out at the top. So it is usually on an N-type substrate with an electrode attached to the P-type layer. So the refractive index of the packaged material should match the index of the semiconductor. All right, the refractive index and packaged material should match the index of the semiconductor. Otherwise, the produced light will get reflected back into the semiconductor, where it may be absorbed and turned into heat, all right, lowering the efficiency. So that's why the selection of the material is very important, and also the shape, so that light doesn't get reflected back, and then the efficiency is reduced. Your brightness will reduce. Okay. This type of reflection also occurs at the surface of the package if the LED is coupled to a medium with a different refractive index, such as a glass fiber or air. So there's two things here. The first is the package of this LED chip. The second is this epoxy dome. So both material must be chosen carefully so that light does not get reflected back inside the chip. So the refractive index of most LED semiconductor is 3.7, is quite high. And so in almost all cases, the LED is coupled into a much lower index medium. So this makes sure that the light does not get reflected back in. So the reflection becomes substantial. So that's why LED, we say it's quite inefficient because of the mismatch of the refractive index. So very high index. Okay, this is 3.7 and the material outside is phosphor or whatever, and the refractive index is low. So that's why a lot of reflection can happen and the efficiency becomes low. So more than half of the emitted light is reflected back at the LED package and package air. So LED and the package, you must cover the chip with something, right? This chip will be covered with the package. So there's first reflection. The second reflection happens here. So two places reflection occurs. Okay. So it is reduced by using a dome shape half sphere package with the diode in the center, so that outgoing light strikes the surface perpendicularly, at which angle the reflection is minimized. And anti-reflection coating may be added as well. So you can add anti-reflection coating here so that light does not get reflected back. Okay, so this is just to explain about refractive index. So at the surface of the chip and also the surface of the dome, you want light which is transmitted out, you want it to refract out more, right? Rather than get reflected back. So that's why you have to play around with the refractive index of two materials over here. Okay. Okay, conventional LEDs are made from a variety of inorganic semiconductor materials. So if you want red, you have to use aluminum gallium arsenide as the active material, green, aluminum gallium phosphate, and so forth. All right. So zinc selenide gives you blue. Silicon carbide as a substrate gives you blue. Sapphire also gives you blue. Okay, if the emitting layer material of the LED is an organic compound. So just now, the active material is a semiconductor. So we call it a semiconductor LED. You can replace the material, the active material, with a organic material. So it's called Organic Light Emitting Diode, or OLED. To function as a semiconductor, the organic emitting material must have a specific bonding structure. The emitting material can be a small organic molecule in a crystalline phase or a polymer. So if it's a polymer material, it can be flexible. Polymer means like plastic. So this kind of flexible LEDs is called PLEDs or FLEDs. Okay, so just more detail about OLED, Organic Light Emitting Diode. So you can see now the TV, right? You have OLED versus LED. And it is used to create digital display in devices, television screen, computer monitors, portable systems, also in smartphones, handheld game consoles and PDAs. So the major area of research is in the development of white OLED devices for use in solid state lighting applications. So you can see here in an OLED, so similarly you have the anode and the cathode, but your emissive layer is made from organic molecule or polymer instead of semiconductors. Similarly, there needs to be a conductive layer also made from organic molecules or polymers. This is a comparison between a LED or a liquid crystal display and a LG OLED. So, sorry, the image is a bit blurry. I just noticed it now. So this structure is complex. OLED is normally a simple structure. And this LED or LCD, it requires a backlight unit, CCFL. And for OLED, it's actually self-emissive. The material itself is self-emissive. And you need a lightning unit or a pixel unit. Similar, both need a lightning unit, and it's also the pixel unit. So you can see OLED is thinner compared to LED. LED, you have more layers. OLED is just a few layers, thinner. PLED, polymer light emitting diode. So it is lightweight, it is flexible, so you can make very thin films. Okay, this is a bendable PLED. Okay, you can see bend with the hand. So extraordinary resolution, you can see from any angle without loss of information. It enables more energy efficiency, consume less power, can be used to make flexible displays, and it offers very high brightness at low drive voltage. So they also ensure glare-free viewing. So basically you have a polymer material over here, and it's very thin such that it's bendable. Superluminescent light emitting diode. So this actually shows the intensity of light versus the wavelength. So for LED, you can see that it's quite a broad spectrum. And for laser, LED is laser diode. They are normally sharp spectrums. So what if you want something in between? So that's when you use superluminescent light emitting diode. So it's in between. That means the intensity is high, but the spectrum is broad. All right, here the spectrum is very thin. Okay, the line width is very thin. Here the spectrum is broad, but the intensity is very low. So you can see the emission of power, right? Here is very broad, and here is very thin. Okay, so SLADs are semiconductor broadband light emitting device. It's spatially coherent and temporally incoherent light source, so it's combined. So this is incoherent, this is coherent. So it's combination of both. So it has a laser light beam output and also speckle-free broadband spectrum and short coherence length. Okay, so the difference between a SLAD and also a laser diode is the way light is amplified. So the light is amplified during advance and output as is, whereas in a laser diode, it is amplified inside the semiconductor and then finally it is emitted out. Okay, that's why it has got a very sharp. It's as though there is it is increasing its power, and then you get a very sharp power out. Whereas for a SLAD, it is just amplified along the way, and you get a very broad spectrum. Okay, so this is SLAD. Okay, now we move on to lasers. Any questions about LED? All sitting now.
No.
Okay, so we move on to lasers. So a typical laser, it emits light in a narrow, low divergence monochromatic beam with a well-defined wavelength. So basically, a laser, you should have a gain medium or the active region. Okay, unlike LED, in laser, you have a pumping source. Something need to be supplied. It must be stimulated. LED is spontaneous because of the material. And that another important thing about laser is there needs to be a reflector or a mirror. So light will be reflected, oscillated back and forth, back and forth, back and forth. It gains momentum and it will be lased out. So in contrast to the incandescent light bulb, menthol, this is menthol. So it emits light all over the area and a wide spectrum of wavelength. So you can see in laser, it's very, very sharp. It is not like a menthol or a bulb where light is spread out, or like a LED, light is spread out. So it's very sharp light. So it has a gain medium, the active region, and we call it optical cavity because it's a region where oscillation happens or amplification happens. And this gain medium can be either a gas, a liquid, a solid, or it can be free electrons with appropriate optical properties. So a cavity consists of two mirrors. It's arranged in such a way that light bounces back and forth. So light bounces, bounces, bounces back and forth. As each time passing through the gain medium, typically one of the two mirrors, the output coupler is partially transparent. The output laser beam is emitted through this mirror. So this part of the output coupler, it allows light to go through. This one does not allow. So light, when it has gained enough momentum, it can go out through this output coupler. Light of a specific wavelength that passes through the gain medium is amplified, which means it increases in power, and the surrounding mirrors ensure that most of the light makes many passes through the gain medium, stimulating the gain material continuously. So when one photon hits the gain medium, since this is stimulated emission, one photon will produce two photons will produce four photons, 4 will become 8, 8 will become 16. So when light travels in the gain medium, the number of photons keep on increasing. So when the number of photons keep on increasing, at one point it gets enough momentum to laser out. Okay. So it makes many pulses through the gain medium, stimulating the gain material continuously. Part of the light that is between the mirrors, that is within the cavity, passes through the partially transparent mirror and escapes as a beam of light. The process of supplying the energy required for the amplification is called pumping. That means we pump the light to go to higher energy. From higher energy, it will deteriorate to lower energy. During deterioration, light is emitted. So this energy is called, if it's supplied as electrical current, we call it injection pumping. Or if it's supplied using a wavelength or another optical source, we call it optical pumping. So actually, I will emphasize on injection pumping. That means using electrical current, but I also have touched a few about optical pumping as well. Okay. More on laser diodes. So the active medium is a semiconductor similar to what is found in light emitting diode. So again, you have a PN junction and it's injected by electrical current. So sometimes we call them injection laser diodes to differentiate them from optically pumped laser diodes. So this is a similar figure like just now, exactly the same. You have the equilibrium band structure. So when you apply the forward bias, the band gap reduces and electrons and holes can recombine in the active region and light is emitted out. Okay. So the next few slides, I'll be showing different types of lasers. So basically, this is what we call an edge emitting. You have the bottom contact, and this red one over here is the active region. So you have P type at the top and you have N type at the bottom. So light is oscillated over here and finally it will be emitted out at the emitting region. This is edge emitting. Okay. So let's look at recombination. All right, just a little physics. So if this is the active region and the length of this active region is about 1 micron, so holes and electrons need to diffuse about 1 micron. So the number of electrons which are recombining, we call it as dN dt. N simply means the carrier, T is time, and this N, number of carriers times with the volume, because this is a physical volume of the chip. And if you take volume times with dN dt, so the volume is given by L times D, right? This is the volume that the carriers need to pass through. And the number of electrons entering the active region is given by I over E. So therefore, we can say that the dN dt is about 10 to the power of 24 electron hole pairs. And this must be equal, the number of electrical current passing through must be equal to the volume of charge carriers. So we call this the current density, right? J. J is I over L2. You bring L2 down here, you bring E up. And normally, the current density is about 10 kiloampere per centimeter squared, the amount of current passing through the active region. Okay, this is if the active region is 1 micron in length, all right, and you get this amount of current. What if you want to do a quantum dot or a quantum well laser? We'll see later. If you reduce this active region length, you'll get a smaller current. And what are the engineering that you need to do to increase the amount of current? Okay, some band gap engineering needs to be done. Okay, so laser diode construction, you have P type, N type, and also the active region for emission. Okay, so in other lasers, the gain region is surrounded with an optical cavity to form a laser. So basically, in a laser diode, it is actually an optical waveguide. I think this one Dr. Abang has covered. What is an optical waveguide? A waveguide normally means light is constrained inside that layer. All right. Why is it constrained? Because the refractive index outside here is lower than the refractive index over here. So what happens is total internal reflection and light remains inside the cavity. Right. So the two ends of the crystal are cleaved to form perfectly smooth parallel edges, forming a resonator. Photons emitted into a mode of the waveguide will travel along the waveguide and be reflected several times from each end face before they are emitted. Okay, Okay, so basically there are reflectors on both ends. So light hits here, then it's reflected back, reflected back, reflected back. But at the same time, it just stays in the cavity. It doesn't go out. Okay. So as the light passes through the cavity, it is amplified by stimulated emission, but light is also lost due to absorption and by incomplete reflection from the end facets. Finally, if there is more amplification than loss, the diode begins to laze. Okay. So some important properties of the laser diodes, it is determined by the geometry of the optical cavity, right? So the vertical direction, the light is contained in a very thin layer. The structure supports only one single optical mode in the direction perpendicular to the layers. In the lateral direction or the edge emitting, this is edge emitting. Vertical means from the top, lasing from the top. Lateral means lasing from the edge. Okay. It is wide compared to the wavelength of light. Then the waveguide can support multiple lateral optical modes, or what we call multimode. So this is single mode, this is multimode. So if it's edge emitting, you can make it into a multimode. So these laterally multimode lasers are adequate in cases where one needs a very large amount of power but not a small diffraction limited beam. For example, in printing, activating chemicals, or pumping. So your printer machine is using a multimode laser. Okay, it doesn't need to be single mode. Multimode can work, not so sharp. So this is the meaning of single mode, only one mode, and the intensity is very, very sharp. Example is laser pointer, right? It's very, very sharp. Multimode, you can see that the beam is very wide. All right, this is the spectrum, very wide, multimode beam. It's used like in laser printers, multimode laser. So in an application where a small focus beam is needed, the waveguide must be made narrow on the order of the optical wavelength. Only a single lateral mode is supported, and one ends up with a diffraction limited beam.
Doctor?
Yes, Ayah.
What about projector? What about projector?
Yes, it is also using a multimode because it's not sharp. Right? If you see a projector, you can see that the spectrum is very wide, right? It's not sharp. You see the laser pointer here is very sharp. This is laser diode because the spectrum is very small. Do you understand? That's how you differentiate single mode and multi-mode. Single mode, the beam spot size is very, very sharp, very, very small. For multi-mode, the beam spot size is very huge. Haris, can you understand?
Yes.
Okay. So such single spatial mode devices are used for optical storage, laser pointers, and also in fiber optics. So optical storage, your RAM and all this is using a single mode fiber. And also in DVD player, all this is using a single mode laser diode. And these lasers may support multiple longitudinal modes and thus can laze at multiple wavelengths, usually at harmonics of the fundamental. Okay. So the emitted wavelength is a function of the band gap of the semiconductor and the modes of the optical cavity. So in general, the maximum gain will occur for photons with energy slightly above the band gap energy, and the modes nearest the gain peak will laze most strongly. So if the diode is driven strongly enough, additional side modes may appear. So this is the main mode, the highest intensity, and sometimes you can have side modes, right? B and C, you know. So these are all side modes at different wavelengths. And some laser diodes, such as the most visible lasers, they operate at a single wavelength, but that wavelength is unstable and changes due to fluctuations in current or temperature. So this is the main one, the highest, but of course at the sides there may be some other, but the intensity is not so high. So what we count as the wavelength is the highest peak. Okay. So due to diffraction, the beam diverges, expands rapidly after leaving the chip. So this is a chip, this is a laser pointer. So when it leaves a laser pointer, it diverges. Okay. And if you want to use it for a particular application, you must use a lens. Okay. You use a lens and you can get a collimated beam so that it doesn't keep scattered out, doesn't keep diverging. right? And if you need a circular beam, you need to use a cylindrical lens, and other optics can be used. For single spatial mode lasers, using symmetrical lens, the collimated beam ends up being elliptical in shape due to the difference in the vertical and lateral divergences. So you can change the light which is coming out. You can use different lenses to change the nature of the lights for different applications. You can collimate it, you can diverge it, you can also converge it using different kinds of lenses. Laser diode types. Okay, so some simple laser diode require high power, and they can usually be operated only in the pulse mode. Pulse mode means on off. There's light, there's no light, there's light, there's no light. So laser diode in general require extensive heat sinking, including the use of diamond heat sink. Wow, you use diamond, you know, because it can dissipate heat a lot. So this shows a simple laser with the driver. So you can see the number of heat sink available. So this is the laser diode anode and cathode. That's laser 1 over here. And you can see this is the TEC, the cooling support system, and the connector, and Peltier cool mounting plate over here. So there's a 10 kilo ohm thermistor, and this shows the laser on status. So the laser chip is very small, but the cooling system is so huge because they want to reduce the amount of temperature. Why? You can see here, this is the lasing wavelength, okay? But when the temperature increases, the wavelength changes. So what happens when the wavelength changes? If you're transmitting data and the data is transmitted at this particular wavelength, when the wavelength changes, the data does not get transmitted. Okay, so that's why it's very important to cool the lasers down so that the emission happens at the same wavelength at the correct intensity. Okay, this shows the light output, the power of the light versus the current. You can see at different temperatures, the wavelength is different, green, blue, and red. And even the output of the power and also the current required is also different. So the cooler it is, the lesser current needed to stimulate light emission. So the hotter it is, the higher the amount of current needed to stimulate light emission. Okay, so that's why lasers always have a cooling system to cool down the temperature. Okay, so just now we looked at P-N junction. Okay, so the next few slides will be talking about how to improve the structure of the laser. This is called a P-I-N double heterojunction laser. So we have an additional intrinsic layer, and the active region is undoped. So when it's undoped, there is fewer impurity. That means there's no charge carrier. When there is no charge carrier, there is a lower non-radiative recombination rate. What's the meaning of non-radiative? It doesn't contribute to the photon. And when there is less, that means this becomes heat. Radiative recombination means heat. And so the threshold current is reduced. So basically, this shows the band gap. All right, this shows the band gap energy. All right, so this is the recombination area for the electrons and holes. So the P and N regions have a higher gap. The band gap energy is higher. So no optical absorption happens here. Lower threshold current needed, and it's more efficient. So as usual, the refractive index is higher in the active region, and this shows the electric field is high in the active region. Okay, and the wavelength of light must be larger than 0.1 microns. Okay, so just a repetition of just now, P, I, and N. So you can see here the band gap becomes lower because you don't have carrier here. So you can make it lower, and the refractive index is higher. So therefore the electric field is also higher. So just now was a single heterojunction laser. Now you can have a double heterojunction laser. You add two P types and two N types. All right. So in these devices, a layer of low bandgap material is sandwiched between two high bandgaps. So although it's P-type, but you can change the bandgap of A and B. Although this is N-type, you can change the bandgap of A and B. So one commonly used material is gallium arsenide with aluminium gallium arsenide. Each of the junction between different bandgap material is called a heterostructure. So this is called a double heterostructure. So because you have material A and material B. So it's like a basic laser, and the advantage is the active region where the free holes and electrons exist is confined to a very thin middle layer. So what does this mean? It means that more electron and hole pairs can recombine and it can contribute to photon production and amplification. So fewer are left out in the poorly amplifying periphery in the outskirts. So in addition, the light is reflected from the heterojunction and is confined to the region where the amplification takes place. So if the middle layer is made thin enough, it acts as a quantum well. This layer over here, if you can make it thin enough, it can become a quantum well. So the vertical variation of the electron's wave function and thus a component of its energy is quantized. So the efficiency of a quantum well laser, or we call it nowadays we have spacer also, is greater than that of a bulk laser because the density of states function of electrons in the quantum well system has an abrupt age. So later I'll explain this in another slide. So lasers containing more than one quantum well is known as a multiple quantum well laser. So multiple quantum well, they improve the overlap of the gain region. So this shows what we call a VCSEL, vertical cavity surface emitting laser. So this design is actually from my postdoctoral work, and these are all the layers involved. So we have the P type, the N type, and this is the active region, which is a multiple quantum well. There are many quantum wells in the active region, and so this is the quantum well region over here. So it's repeated. So many layers over here, and this is the emission of light. Okay. In a quantum cascade laser, the difference between quantum well energy level is used for the laser transition instead of the band gap. Right? You have a fixed energy level for the quantum well, so that is used as a basis for emission. So this enables laser action at relatively long wavelengths, which can be tuned simply by altering the thickness of the layer. I'll explain this more in a subsequent slide. Okay, so we had heterostructure, double heterostructure, now separate confinement heterostructure lasers. So same, you have two different types of P type, two different types of N type, but now you have a quantum well which is material C. Now, if this layer, like just now, the double heterostructure, if the thin layer is simply too small to effectively confine the light, so in order to compensate that, another two layers are added on outside the first three. So these layers have a lower refractive index than the center layers, and they can confine the light effectively because of, remember the N is lower. Almost all commercial laser diodes since the 1990s have been separate confinement heterostructure quantum well diodes. So this is the most common structure for laser diodes. So else than SCH, we can also etch out the MESA. The side here, we etch it out, throw it away. Etch means throw it away. And when we throw this part away is when the electrons and holes are recombining in this region. We avoid the electrons and holes from traveling to subsequent adjacent area. So you can confine the charge carriers and the also the photons in the active region. So you can get excellent lateral carrier confinement. Carrier means electrons and holes. They are limited here only. They don't travel here, so they are only here. And excellent lateral light confinement. So photons, when it's emitted, it only emit from here. They don't go here, so you can have very well control by having the MESA structure. Okay. So separate confinement, all right. Okay, so I wanted to explain the difference between a bulk material, quantum well, quantum wire, and also quantum dot. Okay, so this is density of states in material versus the energy. So the blue color is the bulk material, any bulk material, for example, gallium arsenide or whatever. So you can see that the density of state, the energy is varying when the density of states changes. But when you confine it to a quantum well, two-dimensional, all right, you can see that there's a like a staircase kind of feature where you can see until this density of state, you know that this energy is the same. And then after that, here you can make the energy the same, and then here is the same, and so forth. But when you reduce it to a quantum wire, you can see there's further control of the energy, right? You know that if you want 15 millielectron volts, you know that by using a quantum wire, you can get 15 millielectron volts, okay? But what happens when you use quantum dots? All right, you can see the energy is very discrete, 20, 40, 60, 70. It does not change like the blue color, right? Very hard to control the amount of energy that you want. So that's why quantum dots, quantum wire, and quantum well are very interesting for device engineering, because you can control the energy. When you can control the energy, you can control the wavelength. Okay, guys, understand?
Yes, doctor.
You're sleeping now. Okay, if you don't understand, let me know. Okay, so this is a basis of quantum dot, quantum wire, and so forth. Okay, let's go back to the quantum well laser. Just now it was 1 micron, all right, and the amount of current density is 10 kiloampere. Now remember, quantum well, it becomes smaller, so we pick 0.1 micron. So the current, of course, reduces to 1 kiloampere. You see, from 10 it became 1. If we make it into a quantum well, the quantum well thickness is 0.01. It's about 10 nanometers. So how much will this become? Now we do max. How much?
0.1.
0.1. Yes, correct. So the current becomes smaller. Faris,
Yeah.
Faris still awake? Sini, are you sleeping or awake?
I'm awake, doctor.
Okay, I understand. It's the evening. Kelat, are you still there?
Yes, doctor.
No.
Yes.
Okay. All right. So double heterostructure or quantum well. So this is the active region. All right. So now the depth or the D, the thickness of the active region, from so thick 1 micron, we reduce it to 0.01 micron. It has become very, very small. But what happens when you have only one quantum well? The intensity is very low. Okay. So in order to increase the intensity of the laser, you need to add more quantum wells, 4 quantum wells, 6 quantum wells, 8 quantum wells, and so forth. So when you increase the number of quantum wells, you have a higher optical intensity. Okay. So for single quantum well, the emission intensity is limited by the carrier capture into the well by the band filling. So we add in more quantum wells to increase the power. So the last one is graded index separate confinement heterostructure. So you already have 2 p types, 2 n types, you already have quantum well. Now we change the refractive index gradually. Okay, the refractive index changes gradually. So in single quantum well, it is very thin, you have poor optical confinement. In multiple quantum wells, you vary the quantum well width and you can vary the emission wavelength. So by changing the index, you can vary the emission wavelength. Okay, so this is an extension of the long wavelength vertical cavity surface emitting laser. So it shows the p-type, n-type, and also the multi-quantum well. So the multi-quantum well, it comprises of indium gallium arsenide phosphide, right? And this is the band gap energy 0.734, and it uses a barrier of same material but different molarity. So the band gap is also different because the molarities are different. And the mirrors, there is a top DBR mirror or distributed Bragg reflector mirror, p-type and also n-type. This is to oscillate the light. So the top mirror, the p-type mirror, is made from these two materials, gallium arsenide, aluminum gallium arsenide. And the bottom mirror is made from gallium arsenide and aluminum arsenide. So light is oscillated here and it's emitted at the bottom over here. Okay. So this shows the lasing for different quantum well values. So as we increase from 3 until 8 quantum wells, you can see that the power increases and the wavelength shifts as well. Okay. So with increasing number of quantum wells, the threshold current increases as well. This shows the lattice temperature versus the current. Okay. Okay, I'd like to introduce to you spacer. Spacer is a surface plasmon amplification by stimulated emission of radiation, or what we call a plasmonic laser. So we are done with LED, we are done with laser diodes. So this is the upcoming latest craze in lasing, which is called a spacer. So what is a spacer? A spacer or a plasmonic laser is a type of laser which aims to confine light at a sub-wavelength scale for below Rayleigh diffraction limit of light by storing some of the light energy in electron oscillations called surface plasmon polaritons. So this phenomenon was first described by Berkman and Stockman in 2003. Okay, let's look at this figure over here. So basically light comes through this cadmium sulfide nanowire. It's a nanowire, so it's very small. And surface plasmon is the interaction of light when there is a metal and a dielectric layer. So you can see here that there is a silver layer. Okay, so when light meets the silver layer, a plasmon field is formed. And when it meets this plasmon field, it gets converted to a plasmonic emission. So the input is photons, blue color, and the emission is yellow color, 489 nanometers. So this is a plasmonic laser, is very, very small. You can see here that this thickness is 5 nanometer and here is 130 nanometers, nanoscale lasers. Okay, but and it's all in plasmonic sizes, very, very small. And this shows using a dye. So in the middle here, there's a silver, which acts, which is the requirement for surface plasmon. There must be a metal. So here's a silver core, and it's surrounded with dye molecules. All right, dye molecules over here. And this figure shows the absorbance versus the wavelength. So the gray color shows the dye emission, and the blue color shows the emission for the C6 or the dye. The gray color is the absorbance. And you can see with the presence of the silver nanoplates in the middle here, there is an emission at yellow color over here. Okay, so it's the absorption spectra for C6 and AG, and the overlap between the two causes the emission of the laser. So this is a spacer. All right, surface plasmon amplification by stimulated emission of radiation. Yes? No questions? Okay, I move on. All right, other types of light sources. These are fiber lasers using fiber. This is not semiconductor laser. This is a fiber laser. So basically you have a core and you have a clad. There's an outer clad, there's a jacket. All right, and it's a high power fiber laser, and the gain medium forms the core. So it's not a semiconductor. This is in a fiber. Okay, and but the method is the same. The lasing mode propagates in the core. You have a multi-mode pump. It propagates in the inner cladding layer. Same. There's a mirror and light oscillates and it gets emitted out. Fiber disc laser in the form of a disc, but it's all fibers. All right. And the output for fiber lasers from 100 watts up to 1 kilowatts. Okay, very high power fiber lasers. You also have chemical laser. This is involving chemical reaction to achieve high power and continuous operation. Hydrogen fluoride laser, the wavelength is at far infrared and the power in megawatt range. Excimer laser, this is a chemical reaction involving an excimer, which is a short-lived dimeric or heterodimeric molecule formed from two species of atoms, typically produce ultraviolet light. So commonly used excimer noble gas compounds, argon fluoride, krypton chloride, krypton fluoride. Xe stands for what? Anyone knows? Xenon. Xenon chloride, xenon fluoride,
Menon.
xenon, right? Xenon chloride excimer laser commonly used in dial ozone LIDAR system. This is used in a LIDAR, light imaging and detection system. Single photon source, all right? What is a single photon source? Only one photon is coming out. So this shows a schematic view of an elliptical micropillar. So it's elliptical in shape and it's a pillar, but it's a micropillar in micron size. That's why it's micropillar. Micropillar cavity. So this is the cavity, and the cavity contains a quantum dot for emission. Only one quantum dot. That's why it's single photon. All right. And a bullseye cavity. So here you have a grating, dielectric Bragg grating, and there's a single quantum dot here. Okay. And in both cases, the quantum dot is positioned at the antinode of the cavity with an accuracy of about 20 nanometers. The asymmetry, what's the meaning of asymmetry? You can see here there are lesser number of mirrors, and here there are more number of mirrors. So this asymmetry in the structure causes high efficiency and polarized single photon emission. This was a paper taken from Springer. So this is a single photon source. All right. Fluorescence lamp. I think Faris asked me last week about this. So this is lampu Kalimantan. All right. Those days we used to use it in our house. Now I think almost everybody changed to LED light. And how it works. So you have a central element in a fluorescent lamp. It's a sealed glass tube. So there's a glass tube here. And the tube contains a small bit of mercury. All right, there's mercury inside. That's why if lampu Kalimantan is broken, they say very dangerous because of the mercury. It's poisonous. And also it contains an inert gas, typically argon, and it's kept under very low pressure. So the tube also contains phosphor powder. All right, over here it's covered with phosphor. And the tube has two electrodes. So there's two electrodes over here and there's two electrodes over here. So they are wired to an electrical circuit. Of course, you switch on, current flows through here. And what happens is electrons will start flowing from these two electrodes. They will try to go to this electrode over here. So while the electrons are moving, they will hit the mercury, and when it hits the mercury, they will collide with the gaseous mercury atoms. These collisions excite the atoms. They will excite the mercury atoms, bumping the electrons to higher energy levels. So you have the electrons moving, so they bump into the mercury, and then you get electrons with higher energy levels. So when it goes to a higher level, it must come down to the normal level. So when it's coming down, emission occurs. Okay. So when the electrons return to their original energy level, they release light photons. Okay. So when it's emitted, it hits the phosphorus, and the phosphorus gives it the fluorescent light. Okay. So this is fluorescence lamp. Other light sources, cathode ray tube. Those days, the TV cathode ray tube. So in a cathode ray tube, you have a stream of electrons flowing through, and it's focused using a focusing anode into a tight beam, and then it's accelerated with a accelerating anode. So you have focusing anode and accelerating anode. And this high-speed beam, it hits the other end of the tube. And you can see at this end of the tube, there is a phosphorus screen. So the phosphorus converts the electrical energy into light energy. And the energy level of the phosphorus crystal raises when the electron beams strike it. Again, it goes to a higher energy level. And then when it goes down, so you have an emission of light. So the light which is emitted through phosphorus excitation is called fluorescence. Okay. When the electron beams stop, the phosphorus crystal region regain their original position, and they release a quantum of light energy which is called phosphorescence or persistence. Okay. So plasma screen, this is the latest TV plasma, plasma TV. So so what you have here are small compartments of plasma, right? plasma display. They are tiny cells and they contain noble gases. And each cell is coated with a red, green or blue phosphor, all right, to get the color. And the electrons pass a voltage to a subpixel. So you can see that it's connected to electrodes. Okay, you have address electrodes at the back here. So it's connected to these individual pixels. And free excited electrons in the plasma, they collide with the gas atoms. So the electrodes, they collide with the gas atoms, transferring energy to one of its electrons. As the excited electron in the atom decays, so again same, it goes to a higher energy level, and then when it decays, it releases a photon of ultraviolet light, which is converted to colored light by the phosphor coating. There is a phosphor coating at the front here. You can see a phosphor coating is embedded inside the subpixels. Okay, so this is how a plasma screen works. Spectral output of several types of lasers. So basically semiconductor diodes are here, semiconductor lasers, right? And different types of lasers will have different wavelength, from visible right until infrared, and also in ultraviolet as well. Okay. So here mostly is using a gas, carbon dioxide laser, carbon monoxide, and so forth. Different types of lasers. Laser safety. So if you find a laser which is a class 1, it is inherently safe, and the light is contained in an enclosure. For example, in CD players, it is a class 1 because it's contained inside the CD player. Class 2 is safe during normal use, usually up to 1 milliwatt power. Laser pointer is safe during normal use. That means you don't point to somebody's eyes. Class 3 laser, this is up to 5 milliwatt, and it involves a small risk of eye damage. Staring into a beam for several seconds is likely to cause minor eye damage. It can damage your retina, right? Class 3B, it can cause severe eye damage upon exposure. This is lasers up to 500 milliwatt. And the last one is class 4. These lasers can burn the skin, and in some cases, even scattered light can cause eye or skin damage. So many industrial and scientific lasers that we saw last week, they are actually in class 4 lasers. So they are very dangerous. So normally we advise students to wear goggles, light goggles, to stop the light from hitting their eyes. Okay. So that's all for my class. Do you have any questions?
Doctor?
Yes.
Electron is a negative charge, right? So what about hole?
Hole is a positive charge.
Like proton?
Proton is no charge. Proton is no charge. Proton has got no charge in it. Normally, electrons and holes, they refer to different energy levels, and holes, they are normally in the valence band, which is the lower energy level, and electrons normally reside in higher energy level. Okay, so proton actually, it's part of the nucleus. Okay, it's part of the nucleus. So neutron and proton is inside the nucleus, all right? And electrons, what happens is when electrons, they move from one energy level to another energy level. So their movement causes a, so this is the normal place where they should be. So when they move, they create a void here, right? This place becomes empty, so we call it a hole. Understand, Faris?
Oh, yeah.
Yeah, so when it moves, when electron moves from one energy level to another energy level, so the original energy level where it was, we call it a hole. For example, from lower energy level, electrons, they go to a higher energy level. This was the original, right? So this place now becomes a hole. So the electron now is here. So this one becomes a hole, this one becomes the This becomes negative charge, this becomes positively charged.
Okay.
So a hole is actually to define the absence of electron, the absence. The electron is not there anymore. Okay, so we call it hole. It is not a physical thing. It is just to show the movement of electrons inside the material. Okay, so if you say it's a P type, that means there is less electrons inside the material. And when you have an N type, that means there is a material with a high electrons inside the material, high number of electrons. Is it clear, Faris?
Yeah.
Okay. All right, any other questions? Either you all understand or you all don't understand. Hello? Hello?
No problem, doctor. Just need more reference.
Yeah, I just need more time to understand all these things. The last time I saw this was 5 to 6 years ago.
Okay, all right. It's okay. I think when I record the video, then you can go through and you can understand better. So I'm sorry for last week's one. I thought it was recorded in Teams, but apparently it was not. So I need to redo the recording again. So I'll do it this weekend. So sorry for that.
No problem, doctor. It's okay.
All right. So I'm sorry, but you have an assignment.
Oh.
Okay, but it's a simple assignment. Okay, and I've given you time until 30th of June. Where's your assignment? Okay, so this is the assignment. Okay. Please write a short review about micro and nanoscale. Can you see my screen?
No.
No, doctor.
Oh, okay, sorry about that. I should share my screen. Can you see it now?
Yes, doctor.
Okay.
Yeah.
Okay, so you need to write a short review. So it's just 500 words or maximum 1 page. And you email it to me before 30th of June. And it can be one of these topics, recent developments of micro and or. That means it can be a micron device or it can be a nanoscale device, optoelectronic device, potential applications, and or methods in fabricating. Choose one title. Okay, last week we discussed many applications, right? So if you understand one of it, you can take that and use it as a potential, or you can Google it up. Okay, so this is an individual assignment, so you send to me by 30th of June, just 1 page or 500 words.
100 words.
Boleh tak?
500 words, doctor, right?
Yes.
Okay, so we are supposed to read it up and then just give a summary of what we understand about it, right?
Correct.
Okay,
So yeah.
So we do either for micro or nano, right?
Yes.
Okay,
Either
doctor.
you choose a recent development, potential application, or method in fabricating. Either one.
For micro or nano.
Yes, either ones. Because sometimes you cannot find nano devices, so I accept micro scale devices as well.
Okay, doctor.
Okay. So I've uploaded this in Teams. I'll also upload it in Folio, and you can submit to me by 30th of June. Is that fine?
Yes, doctor. No problem.
Yes, doctor.
Yes,
Okay.
doctor.
All right.
Yes, doctor.
I think that's all for the class, and thank you all for joining. So there's one person who did not join. Azman did not join. and also Yusuf. Faris, do you know Yusuf? Yusuf Iskandar?
Not really, doctor.
You
We
don't know
barely
him.
meet. Yeah.
Okay, because I tried to send him WhatsApp and everything, he does not answer, so I don't know whether what happened to him. You don't know him, is it? Yusuf Iskandar? Muhammad Yusuf Iskandar.
No.
You don't know him. Okay. All right, never mind, no problem. So thank you so much, everyone, for joining.
Thank you, Doctor.
All right. Okay, bye-bye. Have a nice day.
Thank you,
Bye-bye.
doctor.
Take care. Bye-bye.
Thank you, doctor.
Thank you.
Thank you, doctor.
Bye, guys.